Analysis of blood alcohol content using headspace gas chromatography. For this lab, we're going to be using a gas chromatograph with the flame ionization detector to quantify ethanol in an unknown sample. Here I'm just showing you the inside of the GC oven where the capillary column is actually installed. We have the column dimensions, and it says the stationary phase is HP5, which just means that it's 5% phenyl, 95% dimethyl polysiloxane stationary phase. These are our materials for the lab. Solution A is a 10 mg per mil solution of ethanol and water. Ethanol is the compound that we're measuring for. Solution B is propanol, or internal standard, diluted in water. And solution C is propanol, again, just diluted with the ethanol solution A. And then there's the unknown sample that we're going to measure. I have two 10 ml volumetric flasks for reference samples R1 and R2. And then I have a bunch of 25 ml flasks to make the standard dilutions and to dilute the unknown. In addition, we have the headspace vials that we're going to fill about halfway with our solutions and then sample the air above the liquid and actually inject that into the GC. So for some reason the camera was doing some goofy stuff and most of what I recorded looks like some kind of weird time lapse. So all I'm doing here is preparing all of the solutions as described in the handout. There's reference solution 1, which is tenfold dilution of the solution B, which is just propanol, and then reference solution 2, which is the propanol mixed with the solution A. So the reason why we have two reference solutions is basically to see where propanol comes out in the GC column and where ethanol comes out, so that we can associate those retention times with our analytes. And then after that we're doing calibration standards at 0.2, 0.4, 0.8, 1.2, and 1.6 mg per mil of ethanol, and adding 2 milliliters of the propanol solution as internal standards. So the reason you want to use an internal standard in quantitative analysis, especially for doing manual injection on the GC, is to account for any differences between, for one, injection volume and any other minute differences that might vary from run to run. So instead of just looking at straight peak area for the ethanol, we're going to look at relative intensity. And then the unknown is going to be prepared in the same way as the standards, where we add 2 milliliters of the internal standard and then dilute it up to 25 milliliters. The error associated with the 25 ml volumetric flasks is plus or minus 0.06 milliliters. And for the pipette, it's plus or minus 8 microliters, so you can use those numbers to propagate the error for your analyses, since we're not doing replicates. For the reference solutions, the 10 milliliter volumetrics, I didn't catch the error for them, but they're not quantitative, so... And again, I'm only filling these headspace vials about halfway so that I have enough room to sample the headspace above the solution. Here I'm just giving an overview of the GC system. So it's a 7890B from Agilent. The runtime is going to be 2 minutes at 40 degrees oven temperature. I took off the sampling tower. Usually these things have auto samplers on them, but I couldn't find the right size vials that goes into this thing, so we're going to have to do a manual injection with the needle. This is Agilent's Chem Station software that's used to control the GC and edit the method. So I'm just going to go through the method to double check the parameters. I'm keeping the injection source as manual since I took off the auto sampler. These parameters here don't really matter for the ALS since we're doing manual injection again. The inlet, which is where you actually do the injection, is going to be set to 150 degrees Celsius. The bottom it says that there's a 2-to-1 split ratio. The column we're using is HP5 or DB5 polydimethylsiloxane, 30 meters long, 320 micrometer outer diameter, 0.25 micrometer in film thickness. The flow rate is set to 6.46 about milliliters per minute. I believe the carrier gas is helium. The oven is again set to 40 degrees C. It's an isothermal separation. If you want to get fancy, you can do something called a temperature gradient and heat the oven from 40 or 50 C all the way up to the max temperature, like 300 or 350. The flame ionization detector is set to 300 degrees C. Airflow is 450 mils per minute. The hydrogen flow is 30 mils per minute, and the nitrogen flow is 25 mils per minute. These aren't terribly important parameters. These don't affect your calculations at all. It's just good things to know that you have to report whenever you do these kinds of analyses. We're acquiring data at 50 data points per second with the FID. And that's pretty much all the parameters that really need to be mentioned. Here I'm going to be starting the process of doing the injections. I like to clean out the syringe by pumping a few times with just air. And then the Teflon septum is pierced by the syringe, and I'm drawing up about 100 microliters of air, or headspace, from the solution. And fortunately I had the foresight to show you guys what this looks like. I'm not actually dunking the needle into the solution, it's only going into the headspace portion. And then piercing the septum inlet, while at the same time pushing the plunger down, then hitting start on the instrument. And here I accidentally pulled the plunger out of the needle barrel. And this is the most fun part of chromatography, is waiting for the separation to happen and looking at the chromatogram as it develops. By the way, the solution I just injected was reference sample R1, which is a 10-fold dilution of the propanol internal standard. So what this run is going to reveal to us is where propanol elutes on this column. Here I'm just going to show the panel on the GC that counts down how long the method takes. It's counting down from 2 minutes. Once the run is complete, ChemStation puts out a preview report that will integrate and figure out the retention time for the peak for the propanol. For whatever reason, the software that I used to record this desktop was also kind of choppy, so you'll have to bear with it. But the retention time it put out was 0.783 for the propanol. And again, since these were just reference samples to figure out retention time, it's not important what the peak area was. It's not quantitative. Here I'm injecting the R2 sample, which is going to be a mix of the ethanol and propanol, so this will also tell us what the ethanol retention time will be. So if you look at the report for the R2 solution, the ethanol comes out at 0.773 minutes and the propanol came out at 0.883 minutes. Any discrepancies in retention time is probably just from the time between injection and me hitting start on the GC-FID. So after 40 minutes of troubleshooting, I figured out that the inlet had a pressure leak, which wouldn't let it hold pressure, and was also causing some band broadening throughout my calibration curve. So I had to fix that and then redo the calibration curve on the GC-FID. I kind of did these out of order, starting with the 400 mg per mil ethanol solution, then going back to the 200, and then returning to the 800. I'll send everyone, or I'll upload these reports from the calibration runs. So basically, you've seen the entirety of what a GC-FID run looks like. So there isn't really any point to stick around for the rest of this. Yeah. Smash that like and subscribe button.